Hello, welcome. In the previous part of this lecture, we discussed subspaces of vector spaces and linear combinations. In this part, we're going to talk about spanning sets and linear independence. And also, we will talk about span of a set. Let's begin the discussion with the formal definition of spanning sets. Definition: let S be a subset of a vector space V. The set S is called a spanning set of V if every vector V in the vector space V can be written as a linear combination of vectors in the set S. In such cases, we say S spans V. Let's have a look at an example. We want to show the set of these three vectors spans the vector space R3. To show that, we take an arbitrary vector V with components A, B, C from the vector space R3, where A, B, and C are real numbers. It is easy to see that if we multiply the first vector by the constant A and the second vector by the constant B and the third vector by the constant C, we get the vector with components A, B, and C. So any vector V can be written as a linear combination of the vectors given in the set S. So the set S spans the vector space R3. Let's have a look at another example. We want to show the set S with these three vectors spans the vector space R3. Let's see the solution. We take an arbitrary vector V with components A, B, C from the vector space R3, where as previous A, B, and C are real numbers. We want to solve the following equation for C sub 1, C sub 2, and C sub 3. So C sub 1 times the vector V1 plus C sub 2 times the vector V2 plus C sub 3 times the vector V sub 3 equals to the arbitrary vector we have chosen. The augmented matrix for the corresponding system of equations of the above takes the following form. And the row reduction gives the following reduced systems. And here we see the reduced row echelon form of the given augmented system. We identify the pivots which correspond to the variables C sub 1, C sub 2, and C sub 3. Therefore, the solution is given by this expressions. So C sub 1 is equal to negative A plus 4B minus 2C. C sub 2 is equal to 2A minus 7B plus 4C. And C sub 3 is equal to negative A plus 2B minus C. For example, if A equals 1, B equals 1, and C equals 2, then we have C sub 1 is equal to negative 1, C sub 2 is equal to 3, and C sub 3 is equal to negative 1. So the vectors with these components 1, 1, 2 can be written as a linear combination of the given vectors with these coefficients. So C1 times V1 plus C2 times V2 plus C3 times V3 gives the vector with components 1, 1, 2. Similarly, if A equals to 0, B equals to 0, and C equals to 0, then the equation has the only trivial solution, namely C1 equals to 0, C2 equals to 0, and C3 equals to 0, obtained by using these three equations. Therefore, the vector with components 0, 0, 0, namely the 0 vector, can be written as a linear combination of the vectors v1, v2, and v3 with c1 equals to 0, c2 equals to 0, and c3 equals to 0. Let's try another example. The set S with these three vectors v sub 1, v sub 2, and v sub 3 with components as shown does not span the vector space R3. It means that some vectors in the vector space R sub 3 cannot be written as a linear combination of the vectors in the set S. In particular, we can show this vector v with components 1, 1, 2 cannot be written as a linear combination of vectors in S. Hence, the set S does not span the vector space R3. Let's have a look at the solution. We take an arbitrary vector v with components a, b, c from the vector space R3. We want to solve the following equation for the unknowns c1, c2, and c3. The augmented matrix for the corresponding system of equations of the above takes the following form, which, when reduced to row echelon form by applying the elementary row operations, we get this reduced row echelon form, where we identify the pivots which correspond to the variables c sub 1 and c sub 2. The last row shows that the system has no solution if the quantity a minus 2b plus c is not equal to 0. In particular, if a equals to b, b equals to 1, c equals to 2, then we see this number, a minus 2b plus c, is not equal to 0. Namely, it is positive 1. And hence, the vector with these components, 1, 1, 2, is not a linear combination of the vectors in S. Thus, the set S does not span the vector space R3. Let's talk about now span of a set. Definition. Let S be a subset of vector space V. The span of S is denoted by the symbol and is defined to be equal to the set of vectors of this form: C sub 1, V sub 1 plus C sub 2, V sub 2 plus all the way up to C sub n, V sub n, where C1, C2, and Cn are real numbers. In other words, the span of S is the set of all possible linear combinations of vectors in S. If span of S is equal to the vector space V, then we say S spans V, or the vector space V is spanned by the set S. Theorem. If S is a subset of a vector space V, then span of S is a subspace of V. We note here the set S is not necessarily a subspace of V, but the span of S is a subspace of the vector space V. Please try to prove this theorem, or the proof of this theorem will be found in the appendix of this note. Remarks. The set S is a subset of the span of S. Namely, span of S contains all the vectors in the set S. Span of S is the smallest subspace of the vector space V containing the set S, in a sense that if W be any other subspace of the vector space V containing the set S, then span of S is also the subset of the subspace W. It means if W is a subspace of a vector space V containing the set S, it should also contain the span of the set S. In this sense, span of S is the smallest possible subspace containing the set S. Linear dependence and independence. A set S of vectors in a vector space V is called linearly independent if the following vector equation has the only trivial solution. C sub 1 equals to C sub 2 equals to all the way up to C sub n equals to 0. If the vector equation has any non-trivial solution, then the set S is called linearly dependent. Let's try to say it again. A set S of vectors in a vector space V is called linearly independent if the vector equation we see here has the only trivial solution. We observe here, if we set C1 to be equals to 0, C2 to be equal to 0, and all the way up to C sub n equals to 0, we get the equation automatically satisfied. So such an equation always has the trivial solution. Now, if the equation has the only trivial solution, then we say the set S is linearly independent. Otherwise, we say it is linearly dependent. In other words, a subset S of a vector space V is called linearly independent if none of the vectors in the set S is a linear combination of other vectors in the set S. Otherwise, the set S is called linearly dependent. Let's try to explain this with the help of some examples. We want to show that the set S of these three vectors is linearly independent. To show that, we consider the following equation. Now, if we replace V sub 1, V sub 2, and V sub 3 by these three vectors, and the 0 vector by this vector, we get this vector equation. The left-hand side of this equation is simply this column vector, and the right-hand side remains the same. Now, we see that this equation is true if C sub 1 equals to C sub 2 equals to C sub 3 equals to 0. So we see that this equation has only the trivial solution. Hence, the set S is linearly independent. In other words, no vectors in this set is a linear combination of other two vectors in the same set. Let's try another example. Show that the set S of these three vectors is linearly independent, meaning that no vector in this set is a linear combination of the other two vectors. To show that, we consider the following defining equation. As previous, the augmented matrix of this system takes the following form. Now, the formal row reduction gives this reduced row echelon form. This shows that the system has the only trivial solution. C sub 1 equals to C sub 2 equals to C sub 3 equals to 0. Therefore, the set S is linearly independent. One more example. We want to check if the set of these three vectors is linearly independent. To solve the following vector equation, we apply the same procedure as in example 10.2.7 to the following matrix. By reducing it to reduced row echelon form, we finally obtain this form of the augmented matrix. Here we identify the pivots, which correspond to the unknowns C sub 1 and C sub 2. The last row shows that the variable C sub 3 is free. Hence, the system has a non-trivial solution. The reduced row echelon form of the augmented matrix takes this equation form. C sub 1 minus C sub 3 equals to 0, and the second row gives C sub 2 plus 2 C sub 3 equals to 0. Since C sub 3 is free, we can assign it to any real number. For example, we take C sub 3 is equal to 1. Then C sub 1 becomes 1 and C sub 2 becomes negative 2. Therefore, we have this vector equation. This means that we have the same equation hold true, but not all the constants are equal to 0. So this equation says that the set S is linearly dependent. In other words, one of the vectors can be written as a linear combination of the other two vectors. For example, V sub 3 can be written as negative V sub 1 plus 2 V sub 2 from this equation. This shows that the third vector is a linear combination of the first two vectors. We could also have written the second vector as a linear combination of the first and third vectors. Or the first vector V sub 1 is a linear combination of the second and the third vector. As shown here. So this shows the set S is linearly dependent. Remark: if S contains the zero vector, then S is linearly dependent. So any subset S of a vector space V containing the zero vector must be linearly dependent, because the vector equation has non-trivial solution. Namely, we can assign C sub 1 equals to 0, C sub 2 equals to 0, all the way up to C sub k equals to 0, but we can assign C sub k plus 1 to be equal to 1. And we see the equation still holds true. So the equation has at least one non-trivial solution. Hence, the set S of vectors in the vector space V containing the zero vector also cannot be a linearly independent set. So it is linearly dependent. Theorem. A set of vectors in a vector space V is linearly dependent if and only if at least one of the vectors in the set S is a linear combination of other vectors in the set S. The proof of this theorem will be found in the appendix of this note. Corollary. A set S of two non-zero vectors in a vector space V is linearly dependent if and only if one of the vectors is a constant multiple of the other vector. The proof of the corollary simply follows from the theorem 10.2.2. With this, we end the part 2 of this lecture. In the next week, we're going to start with the concept of basis and dimension of a vector space. Thank you.